Okay, today we talk about sensors, and we start from the definition. A sensor is a device in the sense that it performs a function. A device is a system that performs a function that receives a stimulus and responds with an electric signal. So we are here discussing a specific class of sensors, the sensors that are artificially made for a particular technology. Of course, biological sensors behave differently. They do not respond with an electric signal, but in the case of man-made sensors, we typically have a response in terms of an electric signal. So, what are the important words in this definition? Of course, device. As I mentioned, a device is a system which performs a function, that has a function, and the stimulus is the quantity that we want to measure, for example, or a condition that we want to measure. We want to measure the temperature, for example, or we want to measure a condition. We want to know if a person is into the room or is not into the room, or if a display has been touched or not. That we want to measure. And when I say that it responds with an electric signal, I mean that the signal is embodied in a voltage, or in a current, or in a charge. These are the essential electric quantities. As we shall see, the operation of a sensor always requires some energy, and in particular it requires an energy flux, a flow of energy which can go from the system to the sensor or from the sensor to the system depending on the situation. So we have the sensor here, we have the system, the measuring system on the other part. We can have the energy flux in this direction or in the other direction. It really depends on the situation. It is important to observe the energy flux because very often the information runs with the energy. So we need to understand what's the direction of energy, because the flow of information follows the energy. Now, there are other relevant words that we need to introduce just to make some vocabulary. A sensor has to be distinguished from a transducer. Transducer is a word which is in Italian trasduttore. So I'm writing here because the translation is not obvious. What is the difference between sensors and transducer? It's a subtle one, because transducer transforms the information from one type of energy to another type of energy. Okay, so transforms the information from one form of energy to another. So not necessarily in terms of an electric signal. It can be a completely different type. For example, a transducer can transform a force in a displacement if we want, and then, for example, it is useful because if we want to measure the force, since the transducer can transform the force in the displacement, then we can directly measure the displacement, which is going to be proportional to the force. But we just call it a sensor if the final form of the information is an electric signal that can be easily read by an electronic circuit. Okay. For this reason, sometimes you have this situation. Here we have the stimulus. This is not atypical. Then we have a first transducer which transforms the stimulus in a different form, information in the stimulus in a different form, let's say transducer 1. Then we have a transducer 2, which can again transform the information in another form, and then we have a sensor here which transforms from the final form in an electric signal. And then in this case we call this whole system, which contains the two transducer and the final sensor, again a sensor, because by definition it is a sensor. Okay, this is important because just for distinguishing this sensor from the global sensor, we can call it a direct sensor. Okay, it's not necessary as an adjective, but it is useful just to distinguish the final one. And we do not have many direct sensors available, but using different transducer we can obtain a large variety of sensors. So you shall see that many sensors are based on a basic sensor, a direct sensor, plus a combination of transducer. Those are necessary in order to increase the number of quantities that can be, let's say, easily read. There is another word that we need to introduce, which is related to sensor, and is the actuator. Actuator in Italian, well, it's easy to, it's attuatore. And of course, the thing is different, but in some way we can say that the actuator has the reverse function of a sensor. Okay, of course, this doesn't mean anything. It's just a way of say the same thing. Basically, the actuator does exactly the opposite, performs exactly the opposite function of a sensor, transforms an electric signal into a stimulus with a different form of energy. Now, this way, of course, for example, the microphone is a sensor because it transforms the acoustic waves. So a signal in terms of acoustic energy into an electric signal, And the loudspeaker is, by this definition, an actuator because it transforms an electric signal in acoustic waves. Typically, we need to consider that both sensors and actuators are part of, can be part of responsive systems, of systems that interact with the user, and in general also of data acquisition systems. So what's the typical situation of a data acquisition system? Just to show the different roles that sensors and actuators can have. So let's assume this is a system that we want to observe, on which we want to perform some measurements, and on the other side we have the electronic system, the electronic part of the data acquisition system, electronic system. Now we typically might have the following situations. We can have some sensors here. For example, it can be a camera which is observing the system and then requires some type of interface in order to provide the information in a form which is suitable for the electronic system. Then the electronic system typically has on this part a subsystem which can deal with the information from many sensors. From the functional point of view, this would be a multiplexer, so that the different incoming data can be in a time division multiplexing sent to the output. Then at the output we might have an analog to digital converter, and then the data can be sent to the microcontroller, eventually to the memory, or to other peripheral systems. Okay. Then we can have a sensor which is at a contact of the system that we want to measure, and it might be able to already send the data in a form that can be transformed into an analog, into a digital system by the ID. So there's no need for an interface. Other sensors might instead need a specific interface. These interfaces are called, let me just use a different arrow, are called signal conditioning interfaces. They can be separated from the real sensors, or can be, let's say, embedded. For example, they might amplify the signal. They might let's say modify the impedances in order to be able to transmit the system transmit the signal from the system that we want to measure to the electronic system. It really depends on the situation. They are all called signal conditioning interfaces. So this is a remote sensor. These are contact sensors. Then we might have a different situation in which a sensor must also be excited. So there's an excitation circuit which is controlled by the micro, because the signal that we received is responding to an excitation that is provided separately. So this would be an active sensor, in the sense that it has to receive energy from the system in order to provide some information. 1, 2, and 3, according to what I wrote, are passive sensors. In the sense that the sensing operation does not need that some additional energy is provided by the system. For example, if I make for simplicity, for example, a radar system typically is an active sensor. You need to transmit the wave and then to measure the echo. In that case, that would be an active sensor. If you want to all types of sensors which are actually encoding the information in an echo of a sound wave or of an electromagnetic wave are of course active sensors, and on the other hand, in the case of passive sensors, you really directly extract the information that we want to measure. It does not mean that the sensor does not require power supply. It really means that the sensing mechanism does not need that energy is introduced in the system. Of course, in addition to that, we can also have something that is acting on a system. So an actuator, which is directly controlled by the microcontroller and modifies the system, sends a stimulus to the system. Okay, just for completeness, we can have a sensor that is actually not measuring something on the system. This would be an environmental sensor. It's not directly acting on the system that we want to measure. So we're going to look at some of this possibility and at some examples regarding different quantities that we want to measure. Okay, let us continue along the lines that we have discussed up to now, and let us write some words that we have already mentioned here. We can classify the sensors according to different categories, and let me repeat something that I have already said. Of course, we can have passive sensors and active sensors. So this distinction is related to the energy. The active sensors require external power for the sensing mechanism. I made an example already. This would be a radar, for example, or an ultrasound monitor, but also something much simpler, for example, a thermistor. A thermistor is a sensor which is useful to measure temperature, and it is basically a resistor that has a resistance which is dependent on the temperature. Right? It's simple. There are many materials that have conductivity which depends on the temperature. They can have a positive temperature dependence or a negative temperature dependence, depending on the type of material. But of course, if you want, and they are typically used to measure a temperature. One exploits the fact that when the temperature changes, the resistance changes. Of course, such a sensor requires energy, because in order to measure a change in resistance, you need to, for example, apply a current through the resistor and measure the voltage drop. This is the typical way in which one can measure a resistance. And in order to do that, you have to, let's say, spend power. So thermistor is a generic way of saying that this component has the resistance which depends on temperature, either with a positive temperature coefficient or with a negative temperature coefficient. Okay. Then we have absolute or relative sensors. This is a significant distinction. So we can have some sensor that can provide the measurement of a quantity with respect to let's say fixed, an absolute scale. Okay, so measurement with respect to absolute scale. In the case of relative, has the name says, the measurement is related to a specific condition, related to a specific condition. So it's not an absolute measurement. Then another classification is with respect to the conversion phenomena. What is the type of energy conversion that we are exploiting? Conversion phenomenon, let's say the singular. Phenomenon is the singular and phenomena is the plural. Okay. Okay. Then there are many other different types of distinction, but these are probably the most important ones. Okay, how do we discuss the sensors and what are the, let's say, important quantities when we discuss about sensors in general? So we need to consider this fact. We have a stimulus, let's call it small s, and we have an electric signal as a response, an electric signal, and we call it with a large S. This is the response. Then the two things are related by a function f, which is called transfer function. So, for example, if we have a temperature sensor. We have the stimulus, which is a temperature. Here we have the response, the electric signal, which is, for example, a voltage. And then we have an expression, a curve, which relates the voltage to the temperature that we want to measure, which can be something like this. Okay, in general, it is not, this would be something like V equal to F of t. Of course, in general, it is not linear. It can be, it can have more or less any shape. Hopefully, it has just one value for any temperature, but it's also, I mean, it can have also more than one value, and this, of course, it's complicating the matters, but we shall see in a few minutes what happened. So we have this transfer function. Of course, we need to know f to the minus 1, the inverse of the transfer function. Because when we know the inverse, we can obtain the stimulus that we want to know once we have the electric quantity. So, for example, in this case, if we know the inverse transfer function, we obtain the voltage on the sensor, and it's if you consider the previous data acquisition system, this voltage has been transformed in a digital number, which has then been acquired by the microprocessor. So we have the number corresponding to the voltage in memory. If we know the inverse transfer function, from that number we can obtain the stimulus, the value of the stimulus, in this example the temperature that we want to measure. So in some way we need to know this part. Just to add some vocabulary, this is the sensitivity is a quantity that is strictly connected to the transfer function. By definition, the sensitivity is the derivative of the electric signal with respect to the stimulus. So it's the derivative of f for a given, let us call value of the stimulus. So it would be, for example, in this case, the slope of the transfer function in the position corresponding to the value of the stimulus. Let's call it B. Okay. We also have a relative sensitivity, which is sometimes used. Let's call it BR, and that is the derivative of the electric signal with respect to the stimulus divided by the stimulus. Okay, just a few words that I think we need to stress here. Of course, there are many types of transfer function. A typical ideal situation, I would say, is the situation in which the transfer function is a line. So we have a linear dependence between the stimulus and the signal. Also because in that case it is very easy to compute the stimulus once we know the electric signal, because the inverse is, of course, again, a linear function. But it's not the typical case. What is important in any situation is that we need to have, let's say, an analytic expression or a good approximation of a formula which can give us the transfer function and the inverse transfer function. Because of course we need to make a relatively easy computation of the stimulus once we have the electric signal. So in all situations, even if the transfer function is not linear, we need to have a good approximation of the transfer function. In the worst possible case, it can be let's say a linear piecewise approximation, okay, by points, connecting just a few points taken along the curve. But we need to have something. Now, another important issue is calibration. What is the calibration of a sensor? Well, we need to consider the situation that typically occurs, that we have fabrication tolerances that can be of the sensor but also of the interface, which is an electronic circuit, so it can have fabrication tolerances. And these fabrication tolerances basically are responsible for the fact that the actual transfer function is not equal to the nominal transfer function of the sensor. Okay, so this fabrication tolerance make the real transfer function of a specific sensor, of that individual sensor that we are considering, different from the nominal transfer function. This means that we need to the exact word is calibrate. We need to calibrate the sensor. So what does it mean? We need to let's say adjust the actual transfer function and make it to adjust the nominal transfer function and make it equal to the actual real transfer function in order to correctly perform the measurement. So with calibration, what we do is we correct, we modify the nominal transfer function in order to fit the actual transfer function. What it means in this particular case, of course, we have in the software a formula for the inverse transfer function, and by measuring with the reference measurement system a certain number of points along the transfer function, we modify the expression of the inverse transfer function that we have in the software. Okay, so what we need to do is measurement with a reference system of a few points a few points of the transfer function. Of course, you can understand that in order for this to work, we need to have an analytical expression of the transfer function, so that we just need to adjust 1, 2, 3 points, and then we have a complete, let's say, fitting of the curve. Okay, for example, then in the simplest possible case, we know that the transfer function is linear, but we need to adjust the starting point and the ending point. And then if the transfer function is linear, we have a well-fitted line. Okay. This is, for example, what we do. What I do when I'm fitting the tablet here. I'm looking at the right angle, all the angles. Then, assuming that everything is linear, I have the position that is. I mean, I have the sensor that is completely calibrated. Okay, there is another possibility of making a calibration, which is called essentially trimming, and it's let's say the opposite thing. With trimming, we modify the actual transfer function, the actual transfer function, physically in order to fit the nominal transfer function. This is also something that in some situation is done. For example, in the case of the thermistor that I mentioned before, there are thermistors that are sold already calibrated, and in that case, in the case of a thermistor, typically the transfer function is linear. The resistance is linearly dependent on the temperature, but actually there's a procedure which is called laser trimming, and with a laser the resistor is modified so that the transfer function of the resistor is identical to the nominal transfer functions that we want to have. Okay, this trimming is typically done at the level of the manufacturing, at the level of the fab. Okay, the other type of calibration can be done either in the fab or in the when the sensor is actually used. The first type of calibration can also be done periodically by the user. Okay. The first step of calibration can be done in the fab, and typically by writing the coefficient in some ROM in the device, and it's a very common situation. But then there are also situations in which one must do a periodic recalibration, and in that case typically let's say the calibration procedure is simpler and must be, let's say, faster to perform. Okay, so 1 and 2. So the first is a modification of the coefficient. Just to make to put a different name, coefficient calibration. And then the other type of calibration, we call it trimming. Okay. It's important to introduce some words because we need to refer to those words when we are discussing a few sensors. One quantity that is important is the so-called accuracy. In Italian is exactly accuratezza, and it is the highest deviation from the true value of the stimulus at the input. Let us introduce it with an example. Let's assume that this is the nominal transfer function, is a linear one. And you see from the definition that the accuracy is a quantity measured, defined at the input. So let's assume that delta is the accuracy, and here it means that the transfer function actually can be wrong, in the sense can deviate from the true value by a quantity which is delta in one direction or in the other direction. So with respect to the nominal transfer function, the actual transfer function is in this band between the two parallel lines. For example, so you see here, if the actual transfer function is this one, the maximum error in the measurement of the quantity S is smaller than delta. You see, if we measure this electric signal S, then let's assume that the true value is this one, because the blue curve is the actual response of the system, of the sensor. But of course we know the nominal transfer function and we interpret it as this quantity. Okay, so the error that we are making is by definition smaller than delta. So this would be, this is the measured quantity. This is the true value. This is the no, this is the measured value. We need to call it differently. This is the this is the response of the system, the electrical quantity that we have. Of course, we interpret it as this measured value, but this is the true value. Of course, if we have defined the accuracy as delta, we know that the delta is the maximum error that we can make. Okay, and so the accuracy is defined for let's say, a typical commercial product. If I buy a sensor with, let's say, 1 degree, if I buy a thermometer with 1 degree of accuracy, it means that the maximum error that I can make when using the thermometer is 1 degree. So that all the actual transfer functions of all the possible thermometers in the market are within those two bands, within those two lines, in that band. Okay. The accuracy is given post calibration. Is typically considered after calibration. For this reason here I put 0 error on the point that we had calibrated, because I assumed that we had done a good calibration at the extreme ends of the transfer function, but of course the transfer function is not exactly linear as we would like it to be. Okay, this maximum variation of the quantity that we want to measure is also called span. This is the span of the sensor. Sometimes it's also called full span of the sensor, but it's the same quantity. In Italian it would be fondo scala. Okay. Now, the accuracy is given typically in absolute terms, can be given in absolute terms, as in the example that I said before, 1 degree Celsius of accuracy, or it can be given as a percentage of the span. So if the thermometer is from 0 to 100 Celsius degrees, I can say that the accuracy is 1% of the span. It's the same as saying 1 degree in that particular case. Or in some cases is given as a percentage of the measured quantity. There's no standard, so depending on the type of sensor you read the accuracy expressed in different ways. As a percentage of the measured quantity, if you look at the picture that I've shown you, it means that the lines are not parallel, because of course you have a delta which is increasing when the quantity that you measure increases, so you have something like a diverging something like a cone, thing that is becoming larger and larger when S is becoming larger. Or sometimes it can be provided in terms of the output signal, not in terms of the input, but in terms of the output. This is typical in the case of digital sensors, in which one typically mentions the number of least significant bits in terms of accuracy. So one has a 2-bit accuracy or a 4-bit accuracy and so on. There is really no standard, and one has to consider that different possibilities are can be found. Okay. So additional quantities or additional possibilities which are important. One is the hysteresis. Hysteresis. in Italian is Hysteresi. Hysteresi, ok? Dico meglio, l'accento è così, Hysteresi. And what is that? Basically, is the error of a sensor's output when the input signal is reached by different directions. Example, this is the output, this is the stimulus. It's very common. It's much more common than one would expect, the hysteresis. And then this situation typically has there's a sensor. If S is increasing, the transfer function goes like that. But then if we go here and then reduce the stimulus, the transfer function does not pass on top of the previous curve, but it goes the other way. And then it's really cyclical. Then if one increases S, it again goes above the line for increasing S. And then in the other direction, and performs this cycle. This is very typical with magnetic sensors, but not only with magnetic sensors. And it's something that occurs when there are some nonlinearities in the system. Okay. Now, with the hysteresis, typically one defines the maximum error. So the maximum error is the maximum distance from one curve to the other in terms of the input signal. So one really call this distance the maximum distance. One call it H, where H stays for hysteresis. This is much more common than one would expect. So we are introducing yours. This is a very easy one. It's the nonlinearity of a sensor. This is of course only valid for linear transfer functions. Otherwise it makes no sense to define the nonlinearity. Nonlinearity, of course, is a deviation of f, the transfer function, from a straight line. It's an easy definition, but of course the situation is much more subtle because there are different ways of defining these deviations. Let us look at a few of them, and we need to also take into account that there is no standard. So let's assume this is the span. Okay, I'm using generic expressions for the stimulus and the electric signal. You can imagine the situation before, the voltage as a function of temperature and so on. Let's assume this is the span. In the case of a linear sensor, after calibration, one has this part without error and typically the other extreme without error, so that the nominal transfer function is linear. Then the actual transfer function sometimes even if we approximate it as a line, might be different. For example, might be this one. This is after calibration, because as I mentioned, we make the calibration, for example, at the limits of the span. For example, 0 and 100 degree if we're considering a temperature sensor. So in black we have the actual transfer function. And then there are different ways of using of defining the nonlinearity. One possibility is to look at the maximum distance in terms of the input stimulus from the nominal transfer function and the actual transfer function. So the maximum would be something like here, right? So in this case, these are the options for defining a nonlinearity. Let's say first is the maximum difference from the nominal transfer function. Of course, it's always at the input. So the nonlinearity would be this quantity and 1. But in some other cases, there is a point in the span which is particularly important from the application point of view, and then one measures the nonlinearity with respect to, let's say, a linear extrapolation around a particularly relevant point. So for example, one defines this is the most relevant point, one traces the straight line which is tangent to the actual transfer function to the point, because one really wants to measure this part, and then the maximum deviation of the actual transfer function from this straight line is this one, is here. So this would be n2. In this case would be the max deviation from a calibration point let's call it an internal calibration point. Okay. This is a very typical situation. For example, if we again consider the example of a thermometer, used for measuring human temperature, typically it has to be very accurate around 37 degrees, because above and below that it's less important. No, 37 degrees is important because one defines if there is a fever or there is no fever, and then that is the point in which it has to be calibrated, and the rest is less important. So in that case, one defines the nonlinearity in this situation, because the error has to be minimized here. Or in some other cases, you see that one defines the max deviation with respect to this. When I write WRT, I mean with respect to the, let's call it, best straight line. I put it between brackets because is a circular definition. The best straight line is the one which provides the smallest nonlinearity. So for example, in this case, the best straight line, let me draw it with a different color, might be, for example, this one. Let's say in this case the maximum nonlinearity, for example, is N3, which is smaller than in the other 3 cases. So it's a sort of circular definition. It's really important to know, because when one looks at a sensor, then I mean, it really needs to know, one really needs to know in which cases the nonlinearity has been defined, because of course if it's if the use one wants to do of the sensor is different from the standard use the manufacturer has considered, then in that case the actual nonlinearity for its use can be very different from the one which is on the data sheet. Okay, so this is something that one must consider. So we can continue a bit with this. Other definitions. We can have saturation of the sensor. This is easy, I can go fast with that. Again, typically saturation is much more useful for linear sensors, but not only linear sensors. You can have a linear transfer function up to a certain point, linear transfer function, and then after a certain input value you have almost no response. This is the saturation. We have repeatability, which is also called precision. In Italian is precisione, actually that is the word that is used. And it is so it takes into account a different aspect, is the fact that when you repeat the measurement you can obtain in precisely the same conditions different results. Okay, so it takes into account the maximum error, typically is the maximum error, max error, relative to the full span, expressed in percentage. So the repeatability is actually is an error, is the inability to represent the same value in the same conditions. And it really can be due to different aspects. For example, it can be due to noise, it can be due to aging, it can be due to, let's say, plasticity, which is the same of saying some memory that has the material, it does not return to its basic situations. Its basic situation, for example, even if we consider, let's say, simpler type of sensors, not electrical ones, but if you look at a scale, the typical scale that one has at home, of course the spring has some plasticity, and if you go up and down on the scale you never have exactly the same measurement. That is not noise, that is really plasticity of the spring. And of course, with more advanced sensors, one can have it now with accelerometers. It is something that cannot be avoided. So saturation, repeatability. And then the other two important characteristics are the resolution. Resolution in Italian is exactly risoluzione. And this is the smallest increment of the stimulus that can be actually sensed. Because even if we need to consider two aspects. Even if we are considering a continuous transfer function, and even if the sensor is analog, then the resolution is not infinite, in the sense that there is an increment below which basically no different quantities is sensed. Okay, this is true for analog sensors. Of course, it's more easily true for digital sensors, because for digital sensors you have a finite number of bits, and then in that case it's pretty easy to evaluate the minimum quantity that allows you to change the least significant bit. And so in that case the resolution really depends on the number of bits that one has available. So in this case there is a difference. So finally, another quantity that is not defined in a unique way is the reliability of a sensor, and this is of course the capacity of the sensor of working without failure. In qualitative terms, it's easy to say what is the reliability, but when you go to a quantitative definition, things become less easy, in the sense that one typically has to recur to a probabilistic definition. So one express the thing in terms of probability. And in this case, I must say there is no unique way of expressing reliability in terms of probability. So let me just give you a few examples. One can say, okay, one quantity is this one, the MTBF, which is the medium time between failures, before failure. When the one can express it in terms of the average MTBF at max T, at max temperature, for example. This MTBF is medium time before failure. So this is useless. So the average is already in the acronym, so I don't need to. So the median time before failure is something that is obtained statistically from a large ensemble of sensors. It is typically done at max temperature because that is the situation in which the failure is let's say more probable. But sometimes it is expressed as a percentage of properly operating sensors after, let's say, a given time, after a given time at max temperature. For example, I can say 95% of the sensors can work at 100 degrees for 2000 hours. So, and also this one is obtained statistically. Okay, just to mention this fact, so there are other formulas that one can use, so one really needs to read carefully the datasheet in order to understand what does that reliability means and what's the relevance to the use of the sensor that one wants to do. Just as a note here, typically these statistical measurements of reliability are done in very particular conditions. They are all typically done with accelerated stress tests. Because really one cannot wait a few thousand hours in order to verify if the device is working or not. So the typical situation is, for example, that one uses let's say puts the device at operation in conditions of high stress, for example, at a much higher temperature with respect to the one that is typically used, so that the stress is accelerated, and for example the failure occurs after a few hours instead of a few thousand hours. And then one has to have a model which allows to say and to translate, let's say, 10 hours at 200 degrees in terms of how many hours at room temperature, for example. So, and there are ways of, let's say, extracting the dependence of the failure time as a function of temperature, so that one can perform the stress test at high temperature and then obtain the results and translate the results at low temperature. High stress test can be related to temperature, or it can be related to, let's say, operating voltage, operating pressure, depending on the type of sensor. Okay. Right, I would like to stop here. We make a break, and then we start looking at how accelerometers work.